Hello everyone. In this lecture, I'm going to discuss some important operations on automata. So why do we require different operations to be performed on automata? Sometimes what happens, a regular language will be given to you and you realize that this language is the combination of two different regular languages. And in such case, we need to perform or we may require to perform certain number of operations. So generally, in such cases, we need to perform either union operation. So I write like union or intersection or we may need to perform the difference operations. So union we represented like U, intersection we know like mathematical symbol like this, and difference like minus. Now when we require, so I'm taking just one example, and with the help of that example we can understand. So let's say there is a language for which I'm asking you to construct an automata. That language is defined over the alphabet 0, 1. Okay. Here every string in this language either contains zeros which is divisible by 2 or ones which is divisible by 3. Okay. So if I want to construct an automata for a language in which number of zeros are divisible by 2, that means if I consider there is an automata A1 and there's another automata, let's say I'm considering as A2. So A1 I'm considering an automata which is generating or accepting a language where number of zeros are divisible by 2. So that means divisible by 2, number of zeros can be 0 or 2 or 4 or 6, right? So if the number of zeros in the A1 automata can be 0 also, your initial state will be final. Okay. So initial state will be final. You can give any name here. So if I give the name, let's say I give a small name, let's say, so I'm giving here A. Okay. A is my initial state for automata A1 as well as it is the final state because zero number of zeros can occur in this language, right? But then it can either accept 2 zeros, 4 zeros and so on. So there has to be a cycle of even number of zeros. So let's say when a zero is coming, I'm reaching to B, but this B state should not be final. Okay. But when another zero will come, I will come back. So in this way, this loop will maintain the even number of zeros. So 2, then 4, then and so on, right? But what about number of ones in this automata A1? Because there is no restriction on A1, the number of ones in this. So I can apply the loop of ones anywhere. So both the states may have the loop of 1. Okay. Now I'm drawing another automata in which number of ones are divisible by 3. So let's say that is A2. And in this, I am assuming that the state is, let's say, X. So similarly, if there are number of ones are divisible by 3, that means number of ones can be 0 or 3 or 6, right? So if the number of ones can be 0, this initial, which is I am considering state X, which need to be final, it is a final state also. Now when 1 comes, it will reach, let's say, Y state, and Y should not be the final one. Okay, because single one should not be accepted. Then let's say another one comes as input, we are reaching, let's say, Z state. Now Z should also not be final because 2 ones are not getting accepted. But when I'm getting 1 again here, so I can reach to the final state. So in that way, if we continuously traversing this particular loop, initially when nothing is coming, there will be 0 number of ones. When I traverse this loop once, there will be 3 number of ones, then 6, then and so on. Now what about B's? There is no restriction on number of B's, so I can put the loop for B's. So B means number of zeros, the another symbol. So if there is no restriction on number of zeros, I am just putting the loop of that. So these two automatas has been constructed. But in order to construct the automata for this given language, this language, let's say this is L1 language, let me draw the automata. So this language require the union of these two. So when two automatas are given, we can perform a number of operations. First, we need to identify if there are two automatas. If we perform any sort of operations, how many maximum number of states we can achieve. Automata is nothing but the set of state. So if there is, let's say, A1, and A1 is having set of states, like A1 is having A and B, there are two states. And there's another automata which I am saying A2, and A2 automata is having X, Y and Z. Let's say there are three states. So if we do the Cartesian kind of product, the maximum possible number of states will be 2 cross 3, that would be 6. Now if I want to write the possible combination of that, so A can be combined with X, so I write AX, let's say. Then A can be combined with Y, A can be combined with Z. Similarly BX, BY and BZ, right? So 6 states can be constructed. It depends upon the operation. Okay, so that is there. Now if we want to do the union, what will be the initial state? If I am constructing 6 state by combining two automatas, I am assuming A is the initial state of A1, X is the initial state of A2. So wherever both the initial state will occur, A and X, that will become the initial state. Okay, and where it depends upon which operation you are performing, whether union or intersection or something. Based on that, final state will be defined. Okay, so in this case we are performing union, either this or this. No, this is AND, right? So what it is saying is language divisible by, like, number of zeros divisible by 2, and so if this AND is there, that means it is intersection. Both the conditions need to be true at a time. So we are going to perform intersection operation. Okay, so in case we want to perform intersection operation on two languages, the final state will be the state where both final states will be there. So A is the final and here X is the final state. That means AX will become the final one in case of intersection operation. In case of intersection operation. But in case you perform the union operation for some language on automata, let's say A1 and A2, here you can write A2, right? It is not B. So if you are performing union kind of thing, either of the final state can occur. So let's say AX will be the final state. Here A is the final, but Y is not the final state. But then also in union operation, this state will become the final one. AZ will become the final one. Okay. Wherever X will come, BX will also become the final one. Remaining will be non-final. So these are the non-final state, because in both the combination, B is the non-final, Y is the non-final, B is the non-final, Z is the non-final. So these are non-final state. Okay. These four will become the final state in case of union operation. Right. Then if we are performing difference, so let's say if I am performing A1 difference A2, that means we are accepting all these strings, those are in A1 but not in A2. Those are in A1 but not in A2. So we need to accept all these strings. Those can be accepted by A1 but should not be accepted by A2, right? Similarly, if we perform A2 minus A1, then all these strings, those can be accepted by A2 but need not to be accepted by A1. Okay, so let's solve this question first and then we will discuss it further in detail. So I'm just cleaning it. Now in this particular problem, let me draw. So there are 6 states. So I'm drawing these states like AX. So this is one of these state, and then AY and AZ. There is BX, BY and BZ. Okay, initial state is AX, and because this operation is intersection operation, so wherever both these states you are combining, those are final. So A is the final here, X is the final here. That means AX will become the final for this operation. So what exactly we are doing here? A1 intersection A2. We are drawing the automata for that, right? Now you are combining this. So this is the thing. Now when 0 comes on this particular A, so when 0 comes on A, you reach B. Okay, so wherever B, you can draw it. Wherever B is there, right? So on this state, when 0 comes, you are reaching B. But because you are doing intersection, so you check in this A2, when 0 comes, it is on X. So that means this A1 is leading you towards B and this A2 is leading you towards X. So that means BX state, you need to draw an arrow. So from AX to BX, you are reaching by traversing symbol 0. So when 0 is coming, you are reaching here. Similarly, on this state, when 1 is coming, so when 1 is coming on A1, you are at A. When 1 is coming on A2, you are at Y. So AY, you are reaching here. So when 1 is coming, you are moving towards AY, right? Similarly, we can write all the transactions. So on AY, when 0 is coming, A0 is coming B, and on Y, 0 is coming, it is Y. So that means BY. Okay. So you are reaching towards BY from AY when 0 is coming as input. Now on AY, when 1 is coming, A is leading you to A only and Y is leading to Z. So that means AZ. So you are going towards AZ when 1 is coming as input. On AZ state, when 0 is coming, you are at B. On Z state, when 0 is coming, you are Z. So that means BZ. So when 0 is coming, you are going to BZ by considering 0 as input. When A is coming, you are at A. When 1 is coming, you are at A. When 1 is coming on Z, you are at X. So that means AX state you will reach. So AX is here. That means you come back here. So from AZ to AX, by traversing 1, you will reach. Okay, I hope it is clear. Now similarly, you can write for BX. So this is BX. B, when 0 accept, it is on A, and X, when 0 comes, it is on X. So that means you will reach AX. From BX, you will reach AX by traversing 0. Okay. Now when it comes 1 on B, you are at B. When it comes 1 on X, you are at Y. So BY, you will reach from here. So BX, when 1 is coming, you are reaching BY. Okay. Similarly on BY, B will lead you B for 1 and A for 0. So let's draw for 0. So it is leading on B, when 0 is coming, you are at A only, and on Y, when 0 is coming, you are at Y. So you are reaching AY. So you are reaching AY for 0, and when 1 is coming, you are on B only. Here, when 1 is coming, you are at Z. So you are reaching BZ here when 1 is coming, right? So you are reaching BZ. On BZ, look at, so when 0 is coming on B, you are at A, and when 0 is coming on Z, you are at Z. So that means you are reaching AZ for 0. When 1 is coming on BZ, so B for 1 is leading you to B only, Z for 1 leading to X. So that means you are reaching BX. So that means from BZ, when 1 is coming, you are reaching here. Okay. So this is the final automata, because AND operation we were performing. So the final state is only one, where both the final states A as well as X is there. If we perform, let's say, union, if instead of AND, if I write OR, so instead of this AND, let's say I cross it and I write OR here. In that case, the rest of the things, the transactions will be same, but the final states will be wherever the final states of either A1 or A2 occurs, those states will become final. So here A or X both are coming, this will be final. A is here, so this will also be the final. A is here, so this will also be final. And in this, X is the final, so wherever X will come, that will also become the final. So this will. So in union operation, there will be 4 final states. Okay. But in intersection, there will be only 1 final state. Right. So this is sufficient for this lecture. We will continue for more operation in the next class. Thank you. See you in the next class.